evening. When I was young, the biggest telescope in the world was the Mount Wilson 100-inch reflector in a class of its own, and the second largest was the 72-inch metal mirror Ross telescope. Well, things have moved on since then. We had the 200-inch, other large telescopes, and now the largest and most powerful telescope in the world is the VLT, or Very Large Telescope, made up really of 4 telescopes, each with an 8-meter mirror working together, in the best possible site in the Atacama Desert of northern Chile. Well, some years ago, I went there, we did a sky at night from there, and the telescope was being built. Now it's complete, and Chris Lintott has just been there.
I'm standing on the summit of Paranal, and behind me are the 4 domes which house the telescopes that make up the VLT. Each one of them would be a world-class observatory in its own right, but the plan here is to get them to work together, and when that's achieved, we'll have an instrument theoretically capable of seeing a man on the surface of the moon. The site at Paranal in Chile is ideal for astronomy. Rain is extremely rare, and the whole atmosphere is almost completely dry. Not the ideal climate for wildlife, but as we're in the middle of the Atacama Desert, the driest anywhere in the world, literally nothing lives here except the astronomers. Difficult though it is to believe, this is an ancient seabed which has been pushed upwards by the process of continental drift. It bears a striking resemblance to the surface of Mars, as seen in pictures sent back from spacecraft like Mars Express. Red sandy soil, boulders, even the occasional dust devil. I half expect to see the rovers Spirit and Opportunity come rolling over the nearest hill. The unique climate of this place is easily seen in satellite images. Air cooled by the Pacific currents forms an almost permanent cloud cover at sea level, whereas further inland, over the Chilean Andes, the air is cooled enough to form cloud. In the middle, we have perfectly clear nights, 350 days a year.
We astronomers always want to do things better, to go deeper, to look for fainter objects. So when we were satisfied that we had a very good observatory on La Silla, we decided what's the next step, and the next step was to go bigger, and going bigger was the VLT. And the VLT was a major investment for ESO, and in order to maximize the return, we wanted to put it in the best site, and we finally determined that this place was the best for our needs.
So what have been the scientific highlights for you?
Well, there have been a lot of scientific highlights. This wonderful facility has provided us with a lot of new results and very exciting ones. One of those results is definitely, which is very spectacular, is the black hole at the center of the galaxy. We have observed the motions of the stars around this black hole. Stars are moving from day to day, really, and we could determine accurately the mass of the black hole, this distance. And on top of this, we have observed infrared flares from the black hole, which is something that had never been observed before, and which gives us access to a whole new physics. We've also possibly detected a new exoplanet around another star. And so far we have an image and a spectrum which apparently are consistent with the presence of a planet around the other star. We've been observing with incredible details the surface of satellites in the solar system, Titan for instance. And this is also very useful for the people who prepare space missions to those objects.
As you might expect from an area with skies as clear and as dark as those we have here, there's a strong tradition of astronomy among the indigenous people of Chile. In order to recognise these traditions, the 4 telescopes that make up the VLT take their names from those of astronomical objects in the Mapudungun language. And so behind me is Antu, which means the sun, Koyan, which means the moon, Melapal, which means the Southern Cross, the most famous of all the southern constellations, and then Yepan, which translates as the brightest star in the sky. What we don't know is whether they've noticed Venus moving against the background stars, and so we don't know whether they counted Venus or Sirius as the brightest in the sky. Yepan was the last of the 4 telescopes to be brought into full service, and once the enormous dome doors are open, light passes in, reflects off the 8.2 metre diameter primary mirror, goes upwards before hitting the secondary, and then coming back down either to an instrument underneath the main focus or into the giant cameras on either side of the main telescope. Now, although the VLT mirrors are the largest ever built for astronomy, they're very thin, only 18 centimetres. So as the telescope looks down towards the horizon, the perfect shape of the mirror will deform under the effects of gravity. However, because the mirror is thin, actuators and computers underneath the telescope are able to adjust that shape and so the mirror retains its perfect form wherever the telescope is looking. Even on a site as good as Paranal, and with all this technology, we still have the fundamental problem that the telescope must look through the Earth's atmosphere, and it's the shimmering of that atmosphere that causes stars to twinkle, and which affects the precise measurements scientists use the VLT for. Now, using what's called an adaptive optics system, a moving mirror is able to compensate for this atmospheric movement. If you like, the telescope's been fitted with glasses, and the VLT is one of the first telescopes in the world to regularly employ this new technology.
This is a quite new system which was installed in 2001, which is able to correct the atmospheric turbulences. The light first goes on a so-called wavefront sensor, which is also a camera which analyzes the images for distortions. And from this information, a very fast computer is calculating the correction for a deformable mirror, which is a soft mirror with 162 actuators, which is able to correct the image to get a straight one.
I mean, looking through a small telescope, you see the atmosphere moving very quickly. So how fast does your mirror have to move to compensate?
Well, the system is able to correct up to 500 times per second.
Well, it's impressive. Up in the control room, we have a recent example of Jeppen's adaptive optics systems in action. The original image shows stars, but they're blurred by the atmosphere's movement. Apply the adaptive optics, and not only do the images become sharper, but you see all the faint objects in the background of the field of view. Each of the 4 telescopes is already in great demand from astronomers, but the VLT was the first major optical observatory to be built with interferometry in mind from the beginning, and progress is already being made towards combining the light from the 4 giant telescopes. Light from each and every telescope involved must have travelled exactly the same distance by the time it arrives to be combined. That means diverting light into loops in order to delay it, and the length of those loops must be controlled with incredible accuracy, which is what makes optical interferometry quite so difficult. I know the 4 telescopes are working individually and working very well, but you have begun to combine their light.
Yes, well, actually a lot. So already 2 years ago we started with 2 telescopes, combining them. We have currently something like 3-4 nights a month when we use at least 2 telescopes together. We have had, as always, a lot of things to learn. It gets very complicated because these big telescopes need adaptive optics. Also, adaptive optics is a new technology.
Right.
This is working well now. Actually, when we operate with 2 UTs, unit telescopes together, it's something like 40-50 computers involved.
Wow.
It's a lot of things which has to work at the same time, and if one single piece breaks down, the whole system breaks down.
Within a year, the 4 main telescopes will be joined by 4 auxiliary telescopes, like the one in the small dome behind me. They're smaller, but they're able to move across the entire platform to any of the observing locations marked by these white covers. Here, the light will pass down into an optical laboratory where it will be combined with light from the main telescopes. Due to this complexity and the sheer scale of the project, it could be up to 5 years until all 8 telescopes are able to work together. But the scientific gains from the ability to see the universe's finest details make it worth the wait. Of course, even with the best telescope in the world, you need good instruments to get results. Spectrographs, like Symphony here, split the light into its constituent wavelengths, enabling astronomers to calculate the chemical composition of the objects we're looking at, and via the redshift, their distance. We use cameras as well, based on the same technology as that in your digital camera.
The red one is the infrared camera Konica, which, because it's working in the infrared, needs a very cold detector temperature, which is reached by a helium compressor to 22 Kelvin.
That's cold. And of course, on this telescope, Jeppen, we've got one of the newest instruments up on the mountain, which is Symphony. And the exciting thing about Symphony is that it can take spectra across a whole field of view.
Yes, correct. It is only a spectrometer. You can do a 3-dimensional image in one shot, because it analyzes every object with respect to a spectrum.
You pick up a redshift, so you have a distance. So yes. I guess it's the first 3-dimensional astronomical camera.
Yeah, you can say this.
It's sunset, but before the observations can begin, the engineers must get the telescope ready. The light fades very quickly when you're as close to the equator as we are here, but the half an hour or so of twilight we do get is a very busy time up on the mountain. First, the telescope tilts over onto its side, simply to avoid anything falling on it when the doors are opened. It weighs over 400 tons, and it's an incredible sight to be inside the dome watching it move around. Next, the doors themselves open, opening the telescope up to the sky, and then the shutters along the front, which provide shelter from the wind during the night, open one by one. Around the rest of the dome, holes open which allow air to flow freely through the dome and across the telescope. When the night's calm, like tonight, the telescope's surprisingly open to the air, and it's the wind blowing through that not only cleans the mirror, but keeps the seeing absolutely steady. The observers that are involved in tonight's programmes will have applied months ago for their time on the telescopes. The VLT is hugely oversubscribed, so it's important to make the most of every second of darkness. The technology and engineering may be impressive, but it's the science that's the really exciting part.
And that is the VLT, so far in a class of its own and providing fundamental results. So time now, I think, to talk to the people who've actually been using it. So I'd say welcome Dr. Isobel Hook from Oxford, Professor Gerry Gilmore from Cambridge, and Dr. Alan Fitzsimmons from Queen's University Belfast. And all of you have been using the telescope for your different researches. So can I come first to you, Alan, because you've been studying asteroids and you're closest to home. So what exactly is your work with the VLT?
Well, what we've been very interested in is studying precise detail the physical characteristics of asteroids in our own solar system. And in particular with the VLT, we've been interested in a theoretical experiment or a theoretical calculation, which implies that as asteroids rotate and they absorb sunlight and re-emit that sunlight as heat, that very act can actually change how fast they're rotating. And this is important for us because we see, first of all, a lot of asteroids that are rotating very slowly. We see asteroids that are rotating so fast they're on the verge of breaking up into small
But you're dealing,
particles.
are you not, with the, what they call the near-Earth asteroids, those that leave the main asteroid zone and swing very close to the Earth. And these are tiny things, often less than a mile across.
That's right. In fact, the specific asteroid we've been studying is one called 2000 PH5. Now, this is only about 150 meters across, so it's actually quite small, but it does approach the Earth about once a year in July. And when it does so, actually, it's about 15th or 16th magnitude and has actually been observed by amateur astronomers. But within a couple of months, it sinks down to fainter than 21st or 22nd magnitude, and that's why we need the VLT to study it.
What exactly are you trying to find out?
Well, what we want to do is measure its rotation rate very accurately from year to year and see whether or not this theoretical effect of changing the rotation of the asteroid actually occurs. Now, to do that, we've got to measure it very precisely. In fact, we have to measure how fast the asteroid is spinning to better than a millisecond. What we see here is a movie made from the individual images obtained with the VLT of the asteroid 2000 PH5 over a period of just under 2 hours. But if you look at it more closely, one can see it getting brighter and getting dimmer on a regular basis. And this is caused by the asteroid reflecting more or less sunlight as it spins.
If we saw one coming towards us, what can we do about it? Anything?
Well, the first thing we could do is make sure we've got the calculations right, make sure we've got the orbit as accurately as possible. And that's something that's ongoing with all 3,000 near-Earth asteroids that we know of to date. But unfortunately, at the moment, if we spot one coming towards us or on a collision course, then at the moment we have no deflection mechanism in place. Saying that, we would normally have about 10 or 20 years warning, and right now the European Space Agency is looking at possible missions to try and deflect an asteroid, so we have some time yet.
Well, it's fascinating work, and of course quite near home, but there was, when they come to you, Gerry, of course you're looking much further into the universe.
I had the privilege of having the first British run on the VLT, and it's part of a project that we've been doing for a very long time now, which is weighing things. We've known now for nearly 20 years that the universe isn't made of what we see. The stuff we see is almost irrelevant. It's important to us because we're made of it, but it's pretty well uninteresting as far as the universe is concerned. Most of reality is some completely different form of matter, what we call cold dark matter.
What is it?
Well, that's what we're trying to find out, you see, that's the challenge. So we've been working for many years with the available best 4-metre telescopes, particularly the William Herschel telescope in La Palma, and we've pushed that to its limits, and then we were ready to take the next step. And so that's where the VLT comes in. What we're trying to do really is measure how cold is cold. How cold is cold dark matter? And we do this by weighing things. And weighing things is easy. You know how to weigh things. Everybody knows how to weigh things. Essentially, we just measure how fast things are moving. And we know if stars are moving very fast or anything's moving very fast, it takes a lot of weight to hold it back. Otherwise, it will fly away. If stars are moving very slowly, it doesn't take much weight to hold it back. So if I find a little galaxy or a part of a galaxy in which the stars are moving all very slowly, I know that bit doesn't weigh very much. Similarly, if I find a part of a galaxy or a whole galaxy where the stars are moving really fast, then I know that thing weighs a lot. And so by comparing how fast the stars are moving and how much weight that Newton's laws then tell me the galaxy has, with all the stuff I can see, I can work out how much real stuff is there, how much weight is there, and that's the matter.
Which galaxies are you studying particularly? Which types of galaxies?
Well, it turns out that the key to measuring how cold is to find the smallest thing that's got dark matter in it. So we know the universe is full of this stuff. Big clusters of galaxies are totally dominated by it. Even middle-sized galaxies like the Milky Way we now know are totally dominated by it. We also know that things like globular clusters of stars don't have any dark matter in them at all. So something in between is where we first find that stuff. And we're fortunate that there are, in fact, the 7 dwarfs. Actually, that's a slight cheat because we found a new one in the course of this program, so there are now 8 dwarfs. Yeah. But there are 7 and a bit dwarfs, dwarf galaxies orbiting around our own Milky Way, like moons around the Milky Way. And these things have just a small number of stars in them. They're very hard to see. In fact, they're visually under-spectacular, to say the least. You can really have to struggle to find them. But it turns out that these things are almost pure pieces of dark matter. So there's these little stars are whizzing around nearly 100 times faster than they ought to be moving, and they make these little galaxies. So these galaxies are the pieces of dark matter that exist in the universe that we can find only because there are a tiny few stars in them. So what we're doing is measuring how fast these stars are moving and how they're spread out. And from that we can just weigh the stuff. And it turns out in these little galaxies that there's about 300 times as much of this exotic stuff as there is of ordinary matter, that's stuff that makes up stars. And so this is our best place for finding out the first thing we want to know about what it is, which is how cold is cold. And we think we're getting there. And
what are the conclusions you've come to so far?
Well, this is all very new, actually. It's exciting stuff. This is almost a press release here. The amazing thing, we've now done 5 of the 7 of these galaxies, and fortunately for us, they're all very similar. If we got 5 different answers, that would tell us nothing. That would mean that they've all had complicated histories and we still have a real problem. But all 5 of them look the same, and we'll know about the other 2 pretty soon too, in about 2 weeks' time, I hope. And all 5 look the same. In fact, what we see is that the distribution of dark matter in the central regions is really rather smooth. Now, if the dark matter were very cold, it would all fall into the middle. And because the particles aren't moving very far, they just stay in the middle. And so cold stuff would form a real spike, a really dense little centre. Hot stuff, very hot stuff, would be very spread out, like the Earth's atmosphere, it's spread out over kilometres. And in between would be in between. And what we see is in between. And that's really exciting. So we seem to see this stuff spread out characteristically on a scale of about 1,000 light years. Equivalently, I can say that corresponds to a density of about equivalent to 1 hydrogen atom per cubic centimetre. So it's pretty sparse, it's a pretty high vacuum, but in every centimetre in this room there'll be 1 of these particles in it. So they're there, and that means we can start to find them. And also, if I were to convert this into a temperature, the temperature is about 10,000 degrees. So it's not cold by any means, but it's tepid. So the stuff's tepid. And we are, just for the first time, beginning to find out enough to start to say what this stuff might be. And first of all, of course, what it isn't, so we can cross a whole lot of obvious targets off the list.
Well, Isobel, your research takes you even further, doesn't it?
It does. We're doing a project to study the universe itself and its expansion rate. And about 6 years ago, our team and another independent team found a very surprising result, that the universe isn't just expanding, but it's actually accelerating.
Accelerating the universe.
Yes. And Because that was rather a surprise at the time, we've been now embarking on a large project to try and confirm this result and really understand it. So we're doing a project which involves studying distant supernova explosions. And in particular, we're interested in type 1a supernovae, which are so-called standard candles, which means we know their intrinsic luminosity. And that means that if we observe their brightness on the sky, that gives us a measure of their distance.
What's the cause of type 1a supernova? Collapse of a very massive star or the destruction of a white dwarf?
We think it's destruction of a white dwarf that's reached the Chandrasekhar mass limit from accretion from another companion star, and that tips it over the edge and causes it to explode. So we believe that they always explode with roughly the same mass, and that means that they have roughly the same luminosity when they explode, and that's what makes them standard candles.
How far out can you go?
Well, at the moment we're able to observe supernovae out to, in terms of redshift, out to about a redshift of 1.5, which corresponds to about a time when the universe was about a third of its current age. So we're able to look right back across the history of the universe. And what we do is we measure the brightness of the supernova, which tells us the distance, and we also measure its redshift, which tells us how much the universe has expanded since the light left the supernova. And if you combine those two things with a series of supernovae at increasing distances, you actually get a sort of map of the expansion history of the universe. And that's how we're able to trace whether the expansion is going steadily or accelerating as we believe it is now.
When I was born, we didn't even know the universe was expanding. It was before Hubble proved it, which was a long time ago now. And we've certainly come a long way, haven't we, since then?
Well, that's right. There are so many things that tell us. The advance of telescopes has allowed us to discover about the universe over the years and over the decades. And so, for example, if we go back to asteroids, if we look at 60 or 70 years ago, most asteroids were thought of as being lying between Mars and Jupiter in the asteroid belt, and there was one, maybe two objects that were known to orbit around the inner planets, and now we know of over 3,000. In fact, we regard this as a natural state of affairs, that objects are thrown out of the asteroid belt and in towards the sun.
I wonder what we're going to find. One point about the VLT is that from its site in Chile, you have access to the southern sky. And some of the most interesting objects are in the far south, so from England they are inaccessible. Well, Chris has been there, and he's had time to look round the wonders of the far southern sky.